Okay.
Okay, so I will share the screen now. Can everybody see the screen?
Yeah.
Yes.
Okay. So today we're going to talk about the second topic of, like this chapter or this part of the course, which is the differential and multi-stage amplifiers. Actually, today we're going to focus only on the differential amplifiers, and next time we're going to cover the multi-stage, or we solve some problems. Okay. So in this lecture here, we will cover these topics. Introduction about the differential amplifiers. What do we mean by the differential amplifier and how they work? We will study two types of the differential amplifiers, the MOSFET, as usually, okay, like many times we study MOSFET and bipolar junction transistor. In this lecture, actually, we're gonna focus only on the MOSFET differential amplifier, and everything could be repeated again same way in the bipolar junction transistor. Okay. We will study something called common mode rejection ratio to see how the differential amplifier can reject what's called common mode signals. And we'll talk about the differential amplifier with current mirror loads or current source load. We call it active load. And we will study the multi-stage amplifiers later on. So if we start with an introduction about the differential amplifier, we call it sometimes differential amplifier or differential pair, because this kind of amplifier consists of a pair of transistors. So two transistors, bipolar or MOSFET transistors. It's very useful in integrated circuits, mainly in integrated circuits. We use it in integrated circuits rather than discrete components. And one example that uses the multi-stage, the differential amplifier is in the input stage of any op amp. So remember the 741 op amp that we used in the lab. The first stage in this operation amplifier is a differential. Let me just use the laser pointer here. So the first stage is the differential amplifier. Okay. Also in circuits, like in logic circuits, in digital electronics, instead of using a single transistor as a logic gate, like as an inverter or as in an AND or OR gates, we use a differential pair, two transistors, to improve the performance of the circuit. So the differential pair is useful in these two examples, in the first stage of an operation amplifier and in some logic gates, what we call emitter coupled logic gates. This technology was known long time ago, okay, but was not utilized until people start to use the integrated circuits, because it's important to have integrated circuits rather than using discrete components. Okay, so we need the transistor to be perfectly matched. This is the main idea. So in discrete components, if you pick up two transistors, two discrete transistors, similar to the ones that we use in the lab, the 2N3904 or something like this, these discrete transistors, you cannot have them matched. You cannot have them perfectly matched. But if in an integrated circuit, it's easy to have two matched transistors, two identical transistors with the same fabrication, with everything. So this technology was not put in practice until the integrated circuits were fabricated, and the modern technology uses the MOSFET transistor technology and the bipolar junction transistor in integrated circuits. We asked the question, why the differential amplifiers are so well suited in IC fabrication, as I mentioned. Why in IC fabrication rather than the discrete components? Well, the first reason is that the integrated circuit fabrication is capable of providing matched devices, as I mentioned. So you can have matched. If you have two transistors and they are required to be identical, you cannot do this unless you have an integrated circuit, because you fabricate both transistors at the same time in the same process. Also, differential amplifiers, as we're going to see, they are not working alone. You have to connect them to different current sources, another transistor or other transistors, other stages, common collector stage, common emitter stage, output stage. So you have to include other circuits to the operational or differential amplifier. So this requires that you put them in an integrated circuit. Okay, so you need more circuit components in the circuit. Okay. Now the other question is why differential amplifiers are preferred than single-ended. So what we mean by single-ended is all the transistor circuits and amplifiers that we have studied so far in electronics 1 and so far in electronics 2. You have just a single transistor with an input and output, and just that's it. So this is the amplifier. But here, the differential pair or the differential amplifier, as we're going to see, has two inputs instead of one input, similar to the operation amplifier that we work with. So why we prefer having two inputs rather than one input? So the two input amplifier is the differential amplifier. And even with the differential amplifier, you can have also two outputs, not only two inputs, but you can have also two outputs. And the single-ended is one input and one end input, or one terminal in the input and one terminal in the output only. So why we prefer the differential amplifier over the single-ended amplifier? Well, if you look at this circuit here at the bottom, many signals you measure in nature, like similar to the ECG, the electrocardiography signal, and the EEG, when you measure the brain signals, or you measure the muscle signals like the EMG. So all these signals are very weak. Okay, so suppose that you are measuring the heart rate, like the heart beating. This is a heartbeat, right? So you'd like to measure or sense the heart beating of a certain person. So you put an electrode or a sensor on the heart, next to the heart, and you try to measure it. The signal captured by this sensor is going to be corrupted by a large amount of noise, and no way to cancel this noise, right? Because you are picking up the noise and the signal at the same time with the same sensor. Okay, so if you pick up the signal with the noise and then you amplify it, then the output signal will be large signal and large noise. Okay, so you are amplifying the noise at the same time. Why? Because the noise comes from where the noise comes from? The noise mainly comes from the ambient, the surrounding, frequencies and signals, coming from the mains, the power source, the electrical power, wires you have in the building, the wireless signals from the mobile phones. All this, comes and hit the sensor at the same time. So they come from the surrounding area and they hit the sensor at the same time. So the sensor picks up the wanted signal, the weak signal of the heart, plus the noise coming from outside. Well, so you cannot differentiate them. You cannot subtract this from this because you have a single input, right? And at the output, you are amplifying both at the same time. But on the other scenario, if you have a differential input and you have two sensors picking up the signal, one is the ground, for example, and one for the signal. So usually when they measure the heart beating or heart signal, beating signal from a patient or someone, they put one electrode on the heart and the other one far away, like to the leg or to the arm or something, to be the ground, the reference. Okay, now each sensor will pick up, this one will pick up the signal, but this one is not picking up the signal because this is the ground. And the noise will hit both at the same time. So you have here the signal plus the noise, but here you have only the noise because this is the ground. This is the reference. This is your reference. It's not another signal. You're not connecting this next to the heart. This is far away. So at this configuration here, you are picking up the signal and the noise here, and the noise only here. So if you are able to subtract these two inputs somehow and then amplify them, so you subtract them first and then amplify them, then you will subtract the noise because the noise is the same in these two electrodes or two sensors. So you end up with having the signal alone without the noise. So you just remove the signal. So this is a brilliant idea to get rid of the noise. So this is the first answer. Why differential amplifiers are preferred than the single-ended? This is the single-ended configuration. You have a common emitter, common base, common collector transistor with just single transistor. And this is the differential pair, as we're going to see now, with two transistors, for example, two bipolar junction transistors or two MOSFET transistors. So the first answer is this is less sensitive to noise than the single-ended. The second one, if you remember the single-ended transistor amplifier, for the single-ended amplifiers, we used to have coupling capacitors, right? Remember the C1, C2, CE, all these coupling and bypass capacitors. The goal was to isolate the DC or to reject the DC from intervening with the AC at the output, right? Here, as we're going to see, you don't need this. You can directly couple the signal to the transistor without any coupling capacitors. C1 and C2, we are not going to see these anymore. C1, C2, and CE. Why is that? And why is that useful? Because fabricating a capacitor in an IC is difficult. You know, you cannot have a 1 microfarad or these large capacitors. Okay, remember the C1 and C2 and CE was large capacitors. They were in microfarads, not in picofarads. They were in microfarads. So fabricating these large capacitors in integrated circuits is almost impossible. You cannot do this. So we better have a transistor or an amplifier that does not have these coupling capacitors. This could be achieved by the differential pair or the differential amplifier. So these are the two main reasons why we prefer differential amplifier than single-ended transistors or amplifiers. If you have any question or anyone has a question, just raise your hand, or I think there's a button or something that you can click to raise your hand and ask a question. So feel free to ask a question while I'm explaining, okay? Okay, now let's analyze the differential pair. Before we analyze it, we need to see what is the differential, how to construct a differential pair. So instead of having a single-ended transistor like this section here, we have two transistors face-to-face like this, okay? They are connected in one end, which is the source in this case, okay? So they are interconnected through the source, and they are identical. If you divide this circuit into two halves, you'll find them exactly identical. So these two transistors are identical. They are matched. Q1 and Q2 are matched. Means that they have the same process, the same transconductance properties or parameters. They have the same W and L. Everything is the same. So these are, and since they are fabricated in an integrated circuit, then this is possible to have two identical or two very close or matching transistors. This is feasible or possible. Then they are joined together at the source, as you can see, and they are biased by this current source. Okay, so now we learn how to bias. You know, instead of having just VDD or VCC and some resistors, we can bias the transistor through a current source, as we learned in the previous topic. So also you bias the drain through RD, or you can replace, as we're going to see later, you can replace RD with a current source as well. So we can replace, as we mentioned in the previous chapter, that it's preferable to use current sources instead of resistors. Okay, we try to avoid resistors as much as we can in IC fabrications. So we have to bias these two transistors in the saturation region. Okay, that means that they are in active region. They work as amplifiers. Okay, not in cutoff, not in triode region. So we have to avoid the triode region, which is the linear region, linear resistance, I mean. But we bias them in the saturation region. And if you recall from the introduction part, saturation region means these two conditions. Okay, the VGS, so this is VGS, okay, has to be greater than V threshold. So you turn on this transistor. You have to turn on this transistor. If VGS is less than V threshold, the transistor is off. So you have to have this condition here. And this condition means that if you subtract V threshold from both sides, so VGS minus V threshold should be greater than 0, right? And VGS minus V threshold is known as the V over drive voltage, the amount of voltage above V threshold that VGS should be should have for the transistor to be on. So you have to have a voltage here that's at least V threshold. Okay, so if I say that this transistor has a V threshold of 1 volt, then VGS has to be at least 1 volt, which has to be more than 1 volt. So 2, 3, 4 for this transistor, the channel to work to be turned on and works. The second condition, this is not the only condition, this is just condition to turn on the transistor, but is it in the triode region or in the saturation region? To ensure that this transistor is in the saturation region, you have to satisfy this second condition, that VDS, this is VDS, should be greater than V over drive. So this VGS should be greater than V threshold, and VDS should be greater than V over drive. So at least VDS has to be at least VGS or higher, okay? Or if we substitute V over drive with VG minus VT, then VDS should be greater than VGS minus VT. And since VDS is from D to S and VGS is from G to S, so then we can just ignore the S and we say that VD to any point to the ground, VD to the ground, should be greater than VG to the ground minus VT. And if you satisfy these two conditions, then the current at the output, the DC current here, ID, okay, is defined by this equation, okay? Kn prime is the transconductance parameter. It's a fabrication parameter. It's comes by like beta in the bipolar junction transistor. It's a constant that comes with the transistor, and 2 is constant. W is the width of the channel. L is the length of the channel. All this constant, okay, which sometimes you call it K sub n, times the V over drive square. So the output current is a function of V over drive square. And V over drive is VGS minus VT. And VT is constant. So actually ID is proportional to the square of VGS, okay? Because V over drive square is VGS minus VT, so square. So ID is proportional to the VGS square. So you have to remember this as we go through the analysis of the transistor. So this is the basic structure of the MOSFET differential amplifier or differential pair. Okay, now we are going to analyze this transistor or this configuration in 2 modes, okay? The first one is known as the common mode, where we have exactly the same signal applied to the 2 inputs. So now you can see that the differential pair has 2 inputs and has 2 outputs, right? So we're gonna see the behavior of this structure to 2 modes of inputs. The first mode, when you have the exact same signal applied to the 2 inputs. And the second one, we call it the differential mode, when you have 2 different signals applied to the 2 inputs, okay? And we'll measure the output, the differential output or the single-ended output, and we see how much is that. Okay, so the first one is the operation with a common mode input voltage, okay? Now, we apply exactly the same signal to the 2 inputs, and we call them VCM. So the input signal now to this gate is called VCM, stands for V common mode, the common mode voltage. And this is exactly the same common mode voltage, and we have the same polarity. So you have here 1 volt and here 1 volt, 2 volt, 2 volt. So they are exactly the same. So VCM is the same as VG1 is the same as VG2. So VG1 and VG2 are the same as VCM. If you have this, okay, and by the way, common mode here, okay, when do we have this case? When do we have 2 signals are identical, you know, are applied the same at the same time to the 2 inputs? This might happen in 2 situations. The first one, when you have a DC input. This is the DC bias. So when you bias the transistor, you bias this transistor with a VDC here, and you bias this transistor with the same VDC to keep them identical or matched. Okay, and the second common mode signals is when the noise hits these two inputs. Okay, remember we said that this configuration will have the ability to reject this noise. Why? Because the noise hits the two inputs with the same value at the same time, because they are very close to each other. So the noise comes to this part, this terminal is the same as the noise here. So the common mode signal is either the noise coming from the surrounding space or the DC bias of the both transistors. So you can think of it in both ways: the large signal DC bias, or the small signal noise that hits the two terminals. Now we are talking about mainly about the large signal. So assume this is a large signal. This is 1 volt, 2 volt, a high voltage signal. Well, okay, if you have this VCM here and VCM here, then ID1, how to calculate ID1? Well, this transistor is in saturation and this one is in saturation. And if you have a current here, that's I2, and current here, I1, they will meet here and they will constitute the I. So I is I1 plus I2, right? And since these two transistors are matched and are identical, then half of the current will be in this leg and half of the current will be in this leg. So half of the tail current source, this is the current source, we call the tail current source because this is look like an animal with a tail. So the I is the tail current source. Half of this current will be in this side and half of it will be in this side. Okay, so we have ID1 equals ID2 equals I over 2. Okay, also VS. Okay, go ahead.
I just wanted to know, because I don't think I caught that. So the current splits in half because of the equivalent impedances that we ideally have across both transistors, correct?
Yes, equivalent everything. You have RD here and RD here. Okay, VDD here and VDD here. Transistor matched, Q1 and Q2 are matched. So this leg exactly the same as this leg, and you have a voltage here is the same as this voltage. So this half is exactly the same as this half, right? So you would expect that the current here would be exactly the same as the current here.
Okay.
Right?
Makes sense.
Okay. So everything is matched. You know, Q1 and Q2 from the beginning would say they are matched. RD is the same as RD. Okay. Of course, this is impossible to be 100% perfect. You know, like you cannot design RD the same as RD, but since this is an integrated circuit, we can try, you know, like we can have them very close to each other. Also, we cannot 100% design two matched transistors perfectly 100%, but we will do our best to make them because they are fabricated at the same time on the same chip, you know, so the possibility of having them very close to each other is higher than making them discrete components, right? And in the lab, we're going to do them discrete, okay? In the lab, we're going to design two differential pair in the lab using two discrete transistors. Of course, in simulation this time, not in the real physical circuits. So the I1 is the same as I2, and I1 is called ID1, and this is the current here, and ID2 is I over 2 as well. Okay. Now let's see the voltages. So Vs, which is the voltage here, the same as here. So Vs is the same because they are common source or connected, joined in the source, is VCM minus VGS, right? If you do KVL here, so the voltage here is this voltage minus this drop here. Okay. Okay, now let's go back to the current. You know, remember the current equation? We said the current ID of any of the MOSFET transistors equal this constant times V over drive square, right? So let's apply this here. How much is ID? ID is I over 2, right? So ID is I over 2. So whether it's ID1 or ID2 is the same. So equals this constant times V over drive square, okay? And V over drive is VGS minus VT, so this is VGS minus VT square. Okay, let's solve for V over drive square. So for V over drive. So if you take V over drive in one hand, one side, and put everything on the other side, this is what you're going to get. First of all, you cancel this 2 with this 2, and you multiply I, or actually divide I by this ratio here, by Kn prime W over L. So this is what you get. And you take the square root because this is going to be V over drive square. So V over drive is square root of I divided by Kn prime omega or W over L. And if I is constant, then this is a constant, right? If you choose I like 1 milliamperes or 2 milliamperes or whatever, then this is going to be a constant. Okay. Okay. So, and we know that VGS is V threshold plus V overdrive. We said that, as we mentioned here, that to have this transistor in the saturation region, you have to have VGS, which is V overdrive plus V threshold. Okay, here. Then VGS could be defined as V threshold plus this value. Okay. Now, this is just like analysis. You know, we're not reaching anything here. Just we're saying, okay, how much are the currents, the voltages here? You know, we just define. The most important part here is to define V overdrive. Okay. Now, how much is VD1 and VD2? If you go back, how much is the voltage here? Think about it. How to calculate the voltage here, or the voltage here? You have a current I over 2 here, and a current I over 2 here, and we'd like to calculate the voltage here from this point to the ground, and from this point to the ground. And you agree with me that this voltage will be the same as this one, right? Because everything is symmetrical, you know, it's identical. Okay, so how to find the voltage here? If you know that the current in this branch here is I over 2.
It's just times that times the resistance, the current and resistance right there.
No, if you multiply the current times the resistance, this will give you the drop across the resistance.
Oh.
But you know that this is VDD. You have VDD here. This is not ground.
Oh, okay.
Okay, you multiply this by this if this is ground, and this is going to be negative, right? But now this is VDD. Remember the famous formula? VD is VDD minus RD I over 2. So minus the drop, right? So if you'd like to find the voltage here, you subtract VDD minus the drop here. Okay, you don't say just VD is RD times I. No, because this is going to give you the drop here, and this is not ground. So to find the voltage here, you subtract VDD, which is the voltage here, minus the drop here, which is RD times I over 2. Okay, so this is what we have here. So VD1 is the same as VD2 is the same as VDD minus I over 2 times RD. And since VD1 is the same as VD2, okay, if you take the difference between these 2 points, if you put the multimeter probes between these 2 points to measure VD, we call it V output D, okay, so which is VD1 minus VD2, then you're going to get 0 because they are identical, right? VD1 is the same as VD2, and if you measure the differential output, we call it the differential output, is going to be 0. So we say that the differential pair does not respond to, or meaning that it rejects the common mode input signal. So if you have a common mode input signal, it means that the signal is applied the same at this gate and this gate. This differential output will not respond. Yes, everyone will respond. This one will respond to this, and this will respond to this. But if you measure the differential output, this is 0. Okay. Why? Because VD1 is the same as VD2. And this is the idea behind the differential pair, is to reject the common mode signal. Okay. Now, we need to find how much is the maximum and the minimum of the input, common mode input, the VCM maximum and the VCM minimum. So how much is the input here, maximum and minimum, so whether this one or this one? Well, okay, so for the maximum, remember that VCM is the same as VG, right? So VCM max is the same as VG max, which is the same as V threshold plus VD. Why we say that? Remember that VG is VT plus VD. Let's go back here, okay? So VD is greater than VG minus V threshold. So if you send V threshold to the other side, so VG has to be less than VD minus plus V threshold, right? So the maximum of VG is VD plus V threshold, right? So this is why we say the maximum of VG is VT plus V threshold, VD. So V threshold plus VD. And how much is VD? We calculated from this side is VDD minus I2 over RD. So the maximum of the input, common mode input, is V threshold plus VDD minus I over 2 RD. This is the maximum. How about the minimum? Well, let's go to the circuit again. So what is the minimum value of this voltage? Well, the minimum value has to agree with the KVL. If you do KVL here, so VCM equals VGS plus the voltage across the current source plus minus VSS. Okay, so this voltage here equals these three voltages added together, minus VSS minus the current source voltage, plus the current source voltage plus VGS. So if we do this here, so VCM minimum is the DC bias, the negative DC bias, plus the current source voltage, which is this one here, so from VS to the VSS, plus VGS, plus this one. And this has to be minimum, okay? So we just take, as we did here, VGS and substitute VT plus V threshold. Remember that VGS here equals V overdrive plus V threshold, right? From this equation here. So VGS equals V overdrive plus V threshold. So if we substitute VGS here with V threshold plus V overdrive, so this is the minimum value. Okay? So V common mode should not go above this value to keep it in the differential pair, and should not go below this value to keep it in the saturation mode. So if you go above this or below this, you will not be working in the saturation mode anymore. Okay, so let's see example 9.1 from the textbook. Can you see the textbook now?
Yes.
Okay. So let's use these equations to understand, to solve this example, to understand this concept. So we have a MOSFET differential pair, similar to the one that we saw in the slides. Is the same thing here. We have two transistors in a differential pair connection with common mode inputs and a tail current source I with these values. Okay, so we have VDD is the same as VSS, but VSS is negative, and both are 1.5. So you bias this transistor with positive 1.5 and negative 1.5. Okay, so this here is positive 1.5, and this one is negative 1.5. Okay, and you have the constant Kn, the transconductance parameter is Kn prime, which is constant, times W over L is constant. Everything is constant. So this is 4 milliamperes per volt square. And the threshold voltage is 0.5. So you have to have VGS higher than 0.5 for this transistor to work. And the tail current source has a current of 0.4 milliamps, and RD is 2.55 kilo ohms. Okay, and we're going to neglect the length, the channel length modulation, meaning that we are going to neglect RO. So with no RO here, so neglect the effect of RO. Okay, and we assume that the current source I requires a minimum voltage of 0.4 volt to operate properly. So V across the current source I has to be at least 0.4 for it to work. If you reduce the current source voltage, so this is the current source, right? If you reduce the current source, okay, let me just amplify, like magnify this a little. If you reduce the voltage across this current source than 0.4 volt, this current source is not going to work. Okay. So we need to find the following. So number A, find V over voltage, V over drive voltage, VGS, the voltage from gate to the source, and then we need to find these parameters. Okay, VS, VD1, VD2, VD1, ID1, ID2, VD1, and VD2 in case VCM is 0, and next is in case of VCM as 1 volt, and the third time when VCM is 0.2 is negative 0.2 volt. Number E, we need to find the highest permitted value of VCM and the lowest value allowed for VCM. So pretty much we're going to use all the equations that we have driven so far. Okay, so the first part is we need to find V over drive voltage and VGS. Okay, so basically we're going to say that, okay, we're going to use this equation here, right? This one here. Okay, knowing that ID1 and ID2 is the same as I over 2, and knowing all these parameters, then we can find V over drive by substituting to this equation here. Okay, so we know that ID1 and ID2 are the same as I over 2, and I is 0.4. So I1 and ID1 and ID2 will be 2 amperes, 0.2 ampere, milliampere. Then if we substitute this here, you're going to have 0.4. 0.4 is I over 2 equals half Kn prime omega W over L, which is 4 milliampere per volt square. And this is 0.4 milliampere, so the milliampere will cancel with the milliamperes. And then we have V over drive square in this side. So you solve for V over drive voltage, you find it is 0.316. Okay, so V over drive is 0.316. VGS, how to find VGS? We know that V over drive is VGS minus V threshold, right? V over drive is the difference between VGS and V threshold. So VGS is V over drive plus V threshold. Okay, so let me try to use the notation here. I'm not sure if this is gonna. So I write it here. So V over drive voltage is VGS minus V threshold, right? Oh, sorry. Okay. So V over drive is the difference between VGS and V threshold. If you send V threshold to the other side, then you get this equation here. Okay. Okay. Now, let me just delete this. Oh, okay. Okay. Now, we found that VGS is V threshold, which is 0.5, plus V over drive, which is 0.316. So this is the value of VGS. So VGS is always VGS, which is this one here. VGS, this is VGS, is always this value, okay? It's always 0.82. Okay, so now we are done with part A. Part B, given that VCM is 0, we need to find VS, ID1, ID2, VD1, and VD2. Okay, so let's go here. So if you know that this one is 0, so we short circuit this, how much is VS, how much is ID1, how much is ID2, how much is VD1, how much is VD2, okay? So let's go here and analyze this circuit. So this is the situation of A. V common mode is 0, so that means this is 0 and this is 0 because the common mode is applied to both ends, okay? So if this is 0, and we know that this is, remember that this one here is, let me bring this marker. Okay, remember that VGS is this one here, right? VGS, as we calculated just a few minutes ago, is 0.82. Okay, then how much is VS? Well, VS is 0 minus this drop, right? Similar to the VBE. Remember when you have VB and VBE, how to find VE? Here we have VG and VGS, how to find VS? You subtract 0 minus this value here, gives you this value. So VS is going to be minus 0.82. Okay, how much is I1? Okay, well, I1 will be the same as half of I, which is 0.4. So half of it will be here, which is 0.2 milliamperes, and half of it will be here, so it's 0.2 as well. Okay, so the current here is 0.2 milliamperes, and the current here is 0.2 milliamperes. Well, we can find the voltage here directly. How? By subtracting 1.5 minus the drop here gives you this voltage. So if you subtract 1.5 minus 2.5, let me just delete this one here. So minus the drop across the 2.5, which is 0.2 times 2.5, this is going to give you 1 volt. Okay, so this is how to analyze this circuit if both VCM is 0. We repeat the same thing if VCM is 1 volt. If you apply 1 volt here and 1 volt here. Okay, again, this is constant. This is not going to change. VGS is constant. Okay, so if this is 1 and this is 0.82, then how much is the voltage here? You subtract this from this, you get this one. Okay, so 1 volt minus 0.82 equals 0.18. So this is VS. Okay, so this is VS here. Now, how much is the voltage here? Since nothing have changed, like we don't have like any change in the current is the same. This is 0.4, the tail current is 0.4, and this is divided into 2 halves. So you have 0.2 here and 0.2 here. So the current doesn't change. And if the current doesn't change, also the voltage here will not change. So even with the change of the input V and input common mode input, okay, you don't have any change in the output. And this is the main idea between for the differential pair to reject the common mode input. Again, let's do the analysis again. With another case, which is case C, where we apply negative 0.2. So now we're applying a negative voltage. So the idea is to see, when you don't apply anything, you see the output. When you apply a positive voltage of 1 volt, you see the output. When you apply a negative voltage of negative 0.2 volt, and you see the output. Okay. So again, this is not going to change, 0.82 VGS. So VS is this minus this, gives you this value here. So it's negative 1.02. Again, the current doesn't change, and the voltage will not change. Okay. All this as long as you are in the saturation region. Let's check. Are we in the saturation region or not? How to check whether we're in saturation region or not?
Greater
Any
than
answer?
threshold. Greater
Sorry?
than threshold. Greater than threshold.
Exactly. We have to go back to these equations. Okay. Remember these equations? Is VGS greater than threshold or not? Is
Yes.
VDS greater than V over drive or not? So we have to check these two equations. These two conditions has to apply. VGS is greater than V threshold. VDS is greater than V over drive. Let's go back. Let's go to this one. Let's go to, where's VGS? VGS is this one here. This is VGS, right? Is it greater than V threshold or not? How much is V threshold? It was 0.5, right? So it's greater than V threshold. So it's the same for all. So always the first condition is satisfied. And how about VDS? VDS is this voltage here. Okay, is from VD, this voltage to VS. How much is this voltage? Well, this is 1 volt, and this is negative 0.82 volt. If you subtract them, you get how much? You get 1.82. Is this greater than V over drive? Yes, if you go to the V over drive that we have just found, it's how much? It's 0.316. So it's greater. So this is this transistor in saturation mode. How about this one? Okay, the same thing. VGS, how much is VGS here? Is again 0.82, greater than 0.5. How about VDS? This is VD and this is VS. If you subtract this minus this, you are going to get 0.82. 0.82 is higher than 0.316. Okay, and the same thing for the third case. So we have to make sure that the transistor remains in the saturation region. Okay, and here's the analysis. Everything is done. Okay, and okay, let's go to the E. Okay, what's the highest value? What's the highest value permitted for the VCM in this transistor? Okay, we mentioned this in the lecture. Okay. The maximum VCM is V threshold plus VD, or V threshold plus VDD minus I over 2 times RD. So this is the highest value, and this is the lowest value. So let's go back and apply this. So VCM max is V threshold plus VD. V threshold is 0.5, and VD is constant all the time, which is 1. Then VC max should be not go greater than 1.5 volt. And how about VCM minimum? Well, VCM minimum, we have to find V across the current source. Remember, because VCM minimum involves the current source, the voltage drop across current source. And in the text, in the example itself, it says that the minimum value of VCS is, or the current source voltage is 0.4. So we're going to substitute this with 0.4. So minus VSS, which is minus 1.5, plus the minimum value of VCS, which is 0.4, plus VGS, which we calculated before, it's 0.82. If you add these up, you end up with minus 0.28. So that means the VCM should be greater than this value here, negative 0.828, and less than plus 1.5 volt. Okay, so this is an example how to apply or how to use these formulas that we have covered so far. Any questions? Okay. Okay. Now we will move to the second mode. Okay, so remember the first mode was the common mode, right? So common mode. Now we move to the second mode, which is the differential mode. Okay, and instead of applying the same signal into the two inputs, you know, we have applied one signal here, it's the same as this one. Now we apply the signal here different than this one. Okay, and this is one case, like one case where you apply here a voltage and you just ground this one. So this is different than this one. This is why we call it differential input. You know, the inputs are different. They are not the same. maybe this is positive, this is negative, this is positive, this is negative, or this is positive, this is 0, or you can apply whatever you want. Okay, so this signal now is different than this signal, and this is the mode of the signal, the real signal, not the noise or the DC bias. Okay, so if you apply a V differential, input differential in this side and keep this as negative, what you are going to do here is that you make, if V input differential here is positive, okay, now because remember that this voltage here is applied between this and the ground, and this one is ground. So as if V input differential is applied between this input and this input. So this is the difference between VG1 and VG2 is V input differential. If V input differential is positive, that means you have higher voltage in this side than this side, right? So this side has a higher input and this one has a lower input. In this case, you are creating a current here because we know that the current is proportional to the square of V of VGS, right? So if you have a VGS here higher than VGS here, then the current here will be higher than this current. And if the current here is higher than this current, then VD2 will be higher than VD1. Okay, can you tell why? If you have a higher current ID1 than ID2, then VD2 will be higher than VD1. Why is that? This current here, ID1, is higher than ID2. Why ID1 is higher? Because VGS1 is higher than VGS2. And we know that the current ID current here is proportional to the VGS square, and the current ID2 is proportional to the VGS2 square. So if VGS1 is greater than VGS2, then ID1 is greater than ID2. If ID1 is greater than ID2, then VD1 is less than VD2. Is that correct? No answer?
Seems about right.
This is true because if ID1 is greater than ID2, then the drop here across RD in this side is higher than the drop here, right? If this current is higher, then this drop is higher than this drop. So this voltage will be less than this one because this voltage is VDD minus the drop here. And this voltage here is VDD minus the drop. Since the drop here is higher than the drop here, then this VD1 will be less than this one. So imagine VDD is 5 and ID, let's say, let's assume RD and RD are 1, okay? And this is 5. And this is 1 and this is 1. And if you have 2 milliamperes here and 2 milliamperes, this is 1K and this is 1K. So if this is 5, this is 1K and this is 2 milliamps, then how much is the voltage here? Well, would be 5 minus 2 milliamps time 1K, so this is 2 volts. 5 minus 2 volt is 3 volts. Okay, so you have a 3 volt here. Now, if you have a 1K here and a 1 milliamps here, and this is 5, 5 minus 1 times 1 is 1, so 5 minus 1 is 4 volts. So this is 4 and this is 3. So if you have a higher current here than the current in this side, then you have a lower voltage here than this one. Okay, so this is why the difference VD2 minus VD1 is positive. If you subtract this, VD2 minus VD1 is positive. Okay, what I would like to say here that this differential amplifier or this differential pair responds to the differential input. If you have a different input, the output is not 0. Remember the common mode, when you have the same input voltage here and here, the output was 0. But now if you have a different voltages from applied to the VGS1 and VGS2, now VD1 and VD2 are not 0. The difference between them is not 0. It's positive in this case. And if you switch, and put higher voltage in this side and lower voltage in this side, ID2 will be greater than ID1, and VD2 will be less than VD1, so the VD2 minus VD1 is going to be negative. So we are not now concerned about how much, the values, but just the idea. If you have a differential input, you have a differential output. Before, if you have a common mode input, you don't have a differential output. Okay, you have to distinguish between the differential input and the differential output. So this is the differential output means VD2 minus VD1, and the differential input means VG2 minus VG1. Okay, and the common mode input if VG1 and VG2 are the same, so you have a common mode. But if you have a V differential input and an input differential, so you have VG1 and VG2 are different. Okay, if you have VG1 and VG2 are different, then VD1 and VD1 and VD2 will be different, and you'll have a differential output. Okay, in common mode case, you don't have an output. Okay. Now we'd like to find how much is the differential input should be. You agree with me that if this voltage is higher than this voltage, then this current will be higher than this current, right? So we will keep increasing the voltage. Okay. Let's go back a little bit. So if we have this voltage the same as this one, how much is the current here in each leg here? Will be half of this one, right? If both voltages are the same, then half of the current will be here and half of the current will be here. But if you start to increase this one is increasing, then you increase the current here. So you're actually doing something called steering the current. The current now is steered from this side to this side. So you're increasing this one and decreasing this one. But can you reach above I? Can ID1 be above I? No. The maximum, if you increase this to a certain value so that all the current I will pass through transistor 1, this is the maximum. And at this moment, all the current will go here and nothing will go here. So by increasing the voltage here, you are steering the current from Q2 to Q1. And if you do the opposite, if you increase the voltage across VGS2, yes, Karan.
Quick question. So I understand when the circuit is perfectly mirrored, yes, the currents are equivalent and half of I.
Mm-hmm.
But when it is not the same input like we have on the screen right now on page 9, how can it be the same?
No, they are not the same. I didn't say that the currents are the same. If you change the voltage, if the voltages are not the same, if you have a voltage here, for example, 1 volt, and here half a volt or 0.1, then the current here is like, let's say I is 5 milliamperes, right? If you have the voltage here higher than this voltage, then these 5 milliamps will not be divided. This will take 3 and this will take 2.
Okay, got it. Thank you.
And then you increase this one. So this will gonna get 4 and this is gonna get 1. Until you increase, and you keep increasing this until the whole 5 milliamps here will be here and nothing here. Okay. So now you steer the whole current from this side to this side. And you can do the opposite. If you increase this one and you keep decreasing this one, you steer the current from this side to this side. Okay?
Thank you.
No, you're welcome. So now we need to know how much is the maximum and minimum VID that will steer the current from, and you know that the maximum current of ID1 is I, and the maximum current of ID2 is I. Okay, so let's assume that now I apply the voltage here that makes ID1 equals I. We need to find this voltage. Okay, so ID1 now is completely I, so that means nothing is passing here. Okay, we will substitute this in the equation. Remember the equation of, and again, you have to do this and guarantee that both transistors are working in the saturation region. None of them will go off, all will go. Of course, if you steer the current all the way to this one and this one is 0, then you turn this off, but this is the extreme. Okay, So if you steer all the current to this side so that ID1 becomes I, now how much is VID that will make this situation happen? Okay, we will substitute ID1 as I in the equation of the MOSFET transistor. Okay, remember this equation? Half Kn prime W over L times V over drive square. Okay, and now we are talking about Q1, so this is ID1. And ID1, now we assume that we steered all the current here. So nothing is going here. So all the current is going this way. Okay, this is I. Nothing is going here. So how much is this fellow here to make this happen? So we substitute ID1 with I. We substitute V over drive by VGS1 minus VT, V threshold square. Then we solve for VGS1. Okay, so simply we divide this by this, okay, and send VT to the other side. So take the square root and send VT to the other side. We will get this one. So VGS1 has to be V threshold plus this quantity here. And if you remember this quantity here, this is square root of 2 times I divided by Kn prime times W over L. If you remember a few minutes ago, we proved that this is called V over drive without the 2. So V over drive in the common mode equals this without the 2 here. So now if you go back here, we can see that this is nothing but square root of 2 times V over drive, because V over drive is this part here without the square root of 2. So this is V over drive. But again, oh, sorry, this is not the V over drive in this situation. This is the V over drive voltage of corresponds to current I over 2, to the common mode situation, not to the differential mode. So this V over drive is the common mode V over drive voltage. Okay, so VGS1, now we can see that it's V threshold plus square root 2 of V over drive of the common mode. Then VID max, we said that VID, which is the differential input here, this one here, should be VGS1 plus VS, right? This voltage here from this point to this point is VS, which is this one here. Let me just delete this line here. So VID, okay, VID, this one, is VGS plus VS, right? Or actually VS is to the ground. Okay, so KVL here, so VGS1 plus VS. And this should be maximum square root of 2 times V over drive. Okay. Okay, now how about the minimum? Well, will be the same if we do the analysis again. The minimum will be negative this value. So the maximum is square root of 2 times V over drive, and the minimum is negative square root of 2 V over drive. And the currents changes in between, right? So now this here is V input differential, VID. And this here is ID, the output current. But to make them, to normalize them, instead of having them as in values, you know, like absolute values, we normalize them. So we normalize this with respect to I. So this becomes ID over I. And we normalize this with respect to V over drive. So this becomes VID over V over drive. Okay, so if you go back to the equation here, and instead of having here, this current as ID, we divide this ID by I. Okay, and instead of having VID, we take the ratio of VID over V over drive. Okay, the proof of this one is not important. It's a long proof, you know, like to, but the concept is important, you know. Like if you keep decreasing the input voltage VID, you actually increase I2 and decrease I1 until I2 becomes I and I1 becomes 0. If you keep increasing the other side, then I1 will increase and I2 will decrease until they meet at the middle when you have the common mode thing. When you have V input 1 as the same as V input 2, you will have the current I1 and I2 will be 0.5. And if you keep increasing VID, you keep increasing I1 and decreasing I2 until I1 reaches I, like the ratio will be 1. If ID1 becomes the same as I, then the ratio is 1. And ID2 becomes 0. The transition here from this value to this value is not linear, perfectly linear, as you can see. It's an unlinear curve. But this curve have both I1, this one is I1, ID1, and this one is ID2. If you make VID positive, then I1, ID1 is greater than ID2. If VID is negative, then ID2 is greater than ID1. And the maximum you can reach, you cannot go beyond this, is when VID is square root of 2 V over drive negative, the minimum, and the maximum is square root of 2 V over drive as positive. Okay, so yes. Go ahead, Arwasaf.
Okay. You said VID minimum is negative square root of 2 VOV.
Yes.
Okay. Is it because if you move to the other page, is it because you grounded VGS?
Grounded VGS?
VGS2. Like if VGS2 is like a little bit smaller than VGS1, will it still go with the same formula? Like
yes, like see, VID is between this point and the ground, right? This is VID.
Yeah.
Between this point and the ground, right?
Yeah.
And what's the ground?
This
one here.
0.
Is this one?
Yeah, 0.
So as we are doing this, okay, as we are doing this, forget about this one here. So it's like this. And this is VID. Forget about this, forget about this. So we are connecting the input voltage across terminal 1 and terminal 2.
Okay.
Right? So if VID is positive, mean that this one is higher than this one. This one here is higher than this one. If VID is negative, that means VGS2 is higher than VGS1. Right? So you have two inputs and you're connecting across them the input differential, the differential input, VID. If VID is positive, then VGS1 is higher than VGS2 because VS is common, right? So VGS1 will be higher than VGS2. If VGS1 is higher than VGS2, that means ID1 is greater than ID2. And this is what you have here. Oops.
Okay.
So if VDN, if VID is negative, then ID2 is higher than ID1. This is ID2. And this is ID1. So it's just one plot for the two currents. Okay. So if you steer VI differential to the positive side, you make VGS1 greater than VGS2. So that means ID1 is greater than ID2. If you steer the V input differential to the negative, you make ID2 greater than ID1. But the maximum, the two limits, the extreme limits that you cannot go beyond is these two limits. The negative square root of 2 V over drive to the positive square root of 2 V over drive. And the equation that governs this curve here is this one. The proof is not important. It's a long proof. I'm not asking you to memorize it or understand it. Just, understand the concept here. Okay, so you can steer the current all the way to the right side, to the right transistor, this way by applying a positive VID, or steer the current to the Q2 by having negative VID. Okay. Okay, now this curve here, these two curves that we show in the previous slide, by just changing VID. Now, if we keep VID constant and we change V over drive, okay, and how we change V over drive? You go back here, this is V over drive, right? You can change I, you can change the width of the channel, you can change the length of the channel, you can change Kn. So if you change any of these parameters, you change V over drive. So if you keep VID constant and you change V over drive, the curve will do the same behavior, will saturate here, but the slope will change. So now for example, V over drive 0.2, you have this slope here. For V over drive 0.3, the slope is smaller. 0.4, the slope is smaller. But you cannot go beyond these limits here, the positive VID maximum and VID minimum. Okay. Now, in this case, this is normalized, but this one is not normalized because now we are changing V over drive. So this is VID, not VID over V over drive. So this is not normalized. This is just VID. So you can change V over drive and have multiple traces like this. Okay. Now let's do quickly the AC analysis. Now, what we have done before so far is the DC analysis. We apply the DC analysis. We just found the large signal. Now we are gonna do the small signal analysis. Okay. So the small signal analysis. This is the differential pair. Okay, the original circuit. To do the AC analysis, as we mentioned many times, we do three things. First of all, we short circuit all the DC source, right? VDD and VSS will be 0. Second, we short circuit any capacitor, any coupling capacitor. We don't have any here. Okay, this is good. Third point is, do you remember? So we short circuit any DC source. We short circuit any capacitor. Third,
Check for R output and R input.
no, this is the analysis. But to do this analysis, before we do this analysis, we have to do 3 steps to change the circuit from its original to the AC equivalent circuit. We have to short circuit or ground all the DC voltage sources. We have to short circuit any capacitor. We don't have here any capacitor. Third one is to replace the
VGT.
transistor with its T model or hybrid pi model. Okay. So now we do the same thing here. So from here to here, we just did the 2 things. We short circuit this, we short circuit this. So this is going to be 0, and this is going to be 0. And if this is 0, that means also this is 0. Why? Because there is no AC current here. This is a DC current. So we open circuit this, but since this terminal is ground, then this terminal also is ground. So we have a ground here, a ground here, a ground here, a ground here, and we don't have any coupling capacitors, so we don't short circuit any capacitors, and we replace each transistor with its T model. Here we are replacing them with T models. Okay, and VG1, we assume that VG1 has 2 signals: the common mode part plus this is the DC part, and this is the AC part. Okay. And since the VID is connected between both of them, we assume that VID is divided by half. So we have half of this here and negative half of it here. So if you add them up, you get VID. So if you have half of ID here, VID here, and negative half of VID here, then as if you're having plus VID between the 2 of them. Okay. So now let's analyze this. The analysis is straightforward. You have this transistor. The current here is GM times VGS, and VGS is this one here. So VGS is the same as V input, which is VID over 2. So VGS1 is VID over 2. So this current will be GM times VID over 2, okay, because VGS is VID over 2. Then if you would like to find the output voltage, you multiply this current by this resistance, right? And this is ground here, so you don't have to subtract anything, you know, you don't subtract VDD minus, because this is ground. So the output voltage is this current times this resistance times negative, right? Because it's upside down. So the output voltage, V output 1 here, is minus GM times RD VID over 2. Okay, the same thing is here. Okay, but the only difference is that you have here minus VR input differential over 2. Here you have plus, but here you have minus. Okay, so VGS becomes minus V input differential divided by 2, and the current here will be the opposite current, and it will be GM times V input differential over 2 because of the negative. Actually, we instead of multiplying by negative, we reverse the arrow here. So this is going to be GM times VID over 2. And now how much is the voltage here across the output? It's this current times this without negative sign, because now the current is going in the same direction as V. This makes this plus and this is minus. So RD times this, which is GM RD V input differential over 2. So this is V out and this is VN. This is negative and this is positive. If you find the A differential is V output 1, V output 2 minus V output 1. Okay, so this is, let me grab this. I know the time is flying, so we'll finish soon. So this is V output 2 minus V output 1. Okay, of course, these are small letters, you know, these are AC. So if you subtract this minus this is the the V output differential. Okay, so this is V output differential, this one here. And you divide this by V input differential. So if you subtract this minus this, you will get GM V input RD, and if you divide this by VID, this gives you the differential gain. So this is how to find the differential gain from this circuit. And the two main reasons that we prefer, as we mentioned before, the differential pair over single-ended is that they are insensitive to interference, and also they do not need coupling bypass or coupling capacitors, as we mentioned before. Okay, I think there is, yeah, let's stop here this time and we continue next time. Do you have any questions?
Can I ask questions about the lab?
Sure.
Will we have a lab session like on Zoom today?
Yes, yes. I
All
will
right.
give you a circuit, you know, like a multi-SEM circuit to replace, you know, the physical one. Remember that we started last time to do the lab view part of the with the DAC, you know, to do the sequential, you know, the SAR, you know, the part that calculate, you know, the digital to analog converter. Okay, and we were supposed to build the physical circuit, the digital to analog converter physical circuit, and connect it back to the lab view, right? And instead of doing this, we're going to do this in multi-sim. Okay, so I'm going to send you the circuit and tell you how to do it.
Okay, so the pre-lab is still due tonight, right?
Yes, the pre-lab, just send me the file that you created in LabVIEW.
Okay, sounds good. Thank you.
This is what I need from the pre-lab. Okay, just make sure that it's functioning, it's working. You know, the you know, this. Let me go here. Where is it? Anyway, the lab view file that you created last, you know, before the break, just send it to me as the pre-lab, and the final report will be using the multi-sim. Okay.
I have a question.
Sure.
So for the VI, do we need the physical TAQ
For-
Sorry, the
for
sound
setting up the
the
DAQ
sound is
system.
not clear. Can you repeat again?
So do we need the actual DAQ for the VI?
No. Oh, actually, it was better if we have it, but I don't know. Like, can someone go and pick it up from the lab?
I mean, I have one, but I don't know if I can just pass it around to people.
Oh, you have one. Oh, okay. Does anyone else have one?
No.
No.
You only have one if you bought one or took one from the lab.
I took from the lab.
Sorry?
I took one from the lab before we left for break.
Okay, that's good. So how many else you have the DAC, you know, the DAC device? You have two only, yeah? Anyone else?
No.
No.
Okay, so we have two solutions, either like three solutions now. Those who have the DAC can use it, but anyway, we have to switch, you know, the physical circuit to a simulation one, right? So I have two options in mind now: either to switch everything to multi-sim, which I prefer because this course is not programming. I know that LabVIEW is good to understand, and it's important to understand. But for me, this course is more into simulation of electronics. It's not programming. So I'm satisfied with what you have learned with programming the LabVIEW that you did before the break. But it's better to go completely as a simulation. So I prepared the circuit. So I'm gonna send you this circuit with some modules, some ready-made modules that you're gonna use, just blocks. You know, I don't want you to go through the understanding what's going on inside, but you're gonna use them directly, and you're gonna build the comparator and the digital to analog converter of the circuit in multi-sim. Okay, and then you study or you analyze this circuit in multi-sim. Okay, the other way is to do everything in LabVIEW, which, you know, I don't prefer, to be honest. Instead of using the MyDAC or the DAC device, we use a virtual DAC device. This is another solution, but this will be completely programming. It's not, has nothing to do with the electronics. Okay, so I'm gonna send you the files, and we will see how it works. Okay.
So we're still doing the lab then?
Sorry.
Are we still doing this lab then?
Yes, we're going to do this lab. I'm going to send you some files to do it in multi-sim. It's not going to take time. Just you build the multi-sim circuit, and you take the measurements, and just the output will be plotting the characteristic curve. You know, the V out versus Vn.
So you would still like the LabVIEW file that we created as well?
Yeah. Yes.
Okay.
Send it as the pre-lab, and I will give you the marks of the pre-lab based on this file. And the final lab, we're going to do it, as I mentioned, using multi-sim, and then you just take the measurements of the characteristic curve of V out versus Vn. You have to generate a curve similar to the one that is in the file. Okay, the output code versus the input voltage for the multi-sim circuit that I'm going to send to you.
So how do you want us to write the pre-lab or the lab?
No, pre-lab, I don't want you to write anything. Just send me the file.
Okay.
Just send me the LabVIEW file, and you write just the final lab report.
So when it comes to final lab report, like writing it, how do you want us to write it? Because these labs, we've been getting like low scores, and we don't really have a template to how to write it.
Yeah, as we did before, the main point is to have the output, you know, like as I told you, the characteristic curve, the V out, the output code versus the input voltage. And you give me a brief explanation of how this analog to digital or digital to analog to digital converter works. So you will explain based on the circuit that I'm going to send you how it works. So try to collect information about this successive approximation analog to digital converter. block diagram, how it works, briefly explain how it works. And then you explain, you describe the circuit that I'm going to send you, and you put the results of the characteristic curve. Okay, and there are some problems in the circuit. I'll tell you, like, you have to figure out these problems. The circuit is not working perfectly, and you have to figure out what the problem is.
When will you send it out?
I will send it out right now. So we are going to work together. I'm going to show you, like, in the Zoom meeting, I'm going to show you what we need to do exactly. I will tell you how to connect. What blocks that you need to simulate in MATLAB, in Multisim, and I'm going to show you how to connect the circuit in Multisim. So we'll work in the circuit today, and I leave you to the rest of the week to prepare for the final lab report. Okay. Any other questions? Okay, so I'll see you at 2 p.m. today, okay?
Okay.
Okay. Thank you so much. Goodbye.